Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to be just a conceptual video here to describe what I call motion studies here, or studying the motion of an object. And first of all, let me talk about, well, what do I mean when I talk about studying the motion of an object here? So what we're talking about, all right, is the relationship between these four things. I just put P, V, A, and T here, PVAT. The position of an object, the velocity of an object, the acceleration of an object, and time. So what we're talking about, studying the relationship between these things. So, when you're studying the motion of an object here, the first thing you typically do is define a set of coordinates here. So in this example, and for this entire discussion, I'm going to put an x-axis or an x-coordinate right here. I'm going to call this the plus x direction. I usually align it so that when time is 0, x is 0. So when we talk about the position of an object, what we're talking about now is the x-coordinate for the remainder of this video and how that varies. Now, just a quick reminder. So I put the 0 here, meaning that anytime x is positive, the car is over to the right somewhere. Whenever x is negative, the car is over to the left somewhere. And when x is 0, it's here. Whoops. Get rid of some things here. So I got new technology I'm working on here, and I'm still kind of getting it all sorted out. So when you see stuff like this, just ignore it for now. All right, now let's talk about the relationship between position, velocity, and acceleration. So these things are all kind of entangled. They're all related. I usually do this graphically. So for any given problem, there's really 3 graphs you can draw here. All right, and I always do them in the same order. I do the acceleration graph on the bottom, velocity graph up top, position graph highest, and I do that in such a way to help create patterns, and I think that helps people learn this, particularly when you're new to this stuff. Now you'll notice that in a lot of my videos, a lot of times I skip the acceleration part. So if in a lot of the problems you see me do, if the acceleration is known, a lot of times you'll see me just start with the velocity graph and work over to the position graph. But for today, we're going to focus on the relationship between these two and these two. So we're going to start here, the relationship between acceleration and velocity. So, all right, acceleration, if you look at how it's calculated, it's equal to delta v over delta t. And one thing that I'd like to point out is that we can rearrange that and write it, change in velocity is equal to acceleration times delta t. Now, what that means is on a graph, right, if we had an acceleration graph, and let's just say for the moment that acceleration is constant, that graph would look like this out to any time. And it's very important to realize acceleration times delta t on this graph, acceleration is this way, delta t is this way, and the product of the two is an area. So this quantity right here is an area bound between the acceleration and time once you have this thing graphically. Now, in this example, acceleration was constant, but if acceleration wasn't constant, we had some other type of curve, the fact that this area gives you the delta v does not change, which is a very handy thing. That makes this a very powerful method. Now, in most cases, especially if you're taking a college physics class or maybe a calculus-based class, the 2 most common cases are when your acceleration is 0 or when your acceleration is constant. And again, your acceleration can be a function. I'll put a of t here. For this video, I'm going to talk about these 2 cases, and I'll make another video about, all right, well, what happens when your acceleration is some constant. So that's how we go from acceleration to velocity information, using this concept that your change in v is equal to area times your delta t. This will typically allow you to write some sort of function for the velocity. Now, again, I'm discussing this stuff in an algebraic sense. Methods of calculus can be used for this stuff as well, and it's fundamentally doing the same thing. I'm going to keep this video to a conceptual video, though, and again, conceptually, it's an area under the curve thing. All right, let me get rid of this. Now, so that's a little bit about how to go from this type of information to this one. Now let's talk about, all right, velocity graphs. So, imagine we have a velocity graph now. And again, And for now, let me assume the velocity is constant. And your velocity is equal to delta x over delta t. So your delta x is equal to velocity times delta t. Now, if your velocity is constant, right, this is some value, I'm just going to call it v, and then this distance on the graph is your delta t. And notice that v times delta t. V is this dimension, delta t is this dimension, and the product is this area. Now, this is true when your velocity is constant, but it's also true when this is some sort of function, right? This area bound under this curve would give you the delta x for that curve. And this fact is what we use to go from our velocity information to a position function, like x as a function of t equals. So, again, once you have your acceleration graph, it's an area problem typically to derive a function for your velocity, or get your v equation, if you will. And once you have your velocity function and graph, it's another area problem to get your position function and graph. So I'm going to go through two cases in this video here. I'm going to go through the two most common cases in physics. Alright, so I'm leaving some trails all over in these videos, and just, that's not super important here, but let me get rid of some of this here. So again, I'm getting used to new technology, a new screen here, and I don't have the touch screen set up quite the way I want it yet. I'm using the palm rejection to write. I think I'm going to try shutting the touch screen off entirely and use only the pen, but I'm not going to do that right now. Now, again, this video is meant to be a very conceptual video, and to try to minimize confusion, what I'm going to do is I'm going to do numerical examples here. So we're going to start with case 1 here. Acceleration is 0, velocity is constant, and I'm going to imagine it's constant at, say, 10 meters per second. And again, what I'm going to do is do this numerically, because I find, especially when students are pointing out that I think it's easier to understand numerically before you start doing everything a bit more abstractly. Now, we're going to go through our graphs. If acceleration is constant, right, then, and 0, then this would look like this, out to any time t here. Whoops. Out to any time t. Now, you'll notice there's no area. No area, meaning your delta v is 0. And if I actually use that to write an equation, delta v is v final minus v initial is 10 meters per second equals 0. If you solve that for v, you get 10 meters per second, and it's constant. So, our next graph, right, we're up here at 10 units a meter per second, and it's not changing. And this is true out to any time t. Now, hopefully, you could have sketched this graph without going through this area thing. And again, this is an example of some of the things I skip when you watch me go through some of my example videos. But right now that we have this here, and we have a function for it. It's a boring function, right? V equals 10 meters per second. Now, there's no t. That's okay. This is still a function. It's just not time dependent, meaning that for all time here in this example, time's greater than 0, your v is 10 meters per second. Now, as far as how do we go from this graph to this graph, again, it's an area problem. Your delta x is going to equal velocity times delta t, which again is, and I want you to think about this in terms of this area. Your velocity is this dimension on the graph right here, which is 10 meters per second. And then this dimension is what we're calling t. Now, delta x is x final minus x initial, and we look here and we note that at t equals 0, x is 0. I'm going to leave the units out. I'll put NCU for note consistent units. So we get x equals 10t. That's a linear function, slope 10. And you can see that again, the palm rejection is not working perfectly. This is not relevant stuff here. I'll work on fixing that for my future videos here. right, so this is some sort of function like this, and the equation for that is x equals 10t. Now, how did I draw that? Well, remember, when your velocity is constant, your position graph will be linear. So there's an example of going from acceleration to velocity, both graph and a function to describe it, using the area under the curve, which in this case is 0. And then going from your velocity graph and the area under the curve to a position graph and a function to describe it. All right, next we're going to do next most common case, constant acceleration. Now, what I'm going to do here, believe it or not, is open a new picture. I save this. Give me a moment here. Save changes, no. There we go, right back to this. A couple things to clean up. We don't need this. And we're going to do case 2. And again, I want to keep this to be a conceptual video here, so I'm going to keep it simple and numerical. Case 2, we're going to look at a constant acceleration example. And in this example, we're going to imagine this car starts from rest, so our initial velocity is 0, and accelerates at, say, 3 meters per second. And we're going to go through and look at graphs and derive functions for acceleration, velocity, and our position, which I'm going to call x. And again, the first thing you typically do is put in a 0. So this is what we're going to call x equals 0. Positive x direction to the right. Motion diagram never hurts. Remember my digital camera, click, 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 taking snapshots. I think I forgot that in the previous example. And again, these are delta x's. These are changes in position during little time intervals. And in this case, our delta x's would be getting larger because the car is moving faster and faster. All right, now, typically we usually want to start here with our acceleration graph. So this car, the acceleration is 3 meters per second, and it's not changing. So meaning a second later, it's still 3. A second later, still 3, out to any time t. Now again, how do we use this graph to derive a function for this? Now remember, acceleration's delta v over delta t. You can rearrange this and write it. Your delta v is acceleration times delta t, and here's the important thing to notice. Your acceleration on this graph is this dimension right there, that distance, which in this example is 3. Your delta t on this graph is this distance on the graph, and the product of the two is this area here. You always want to think of area under this curve here. So our delta v, which is going to equal v final minus v initial. Now in this example, I said let's assume v initial is 0. Again, this is a conceptual video, trying to keep it relatively simple, equals our acceleration, 3 meters per second. I'm going to just leave the units over here. 3 times t. And again, that 3 has units of meter per second squared. And when we multiply that by time in seconds, we'll get something with meter per second, so it's a velocity. Now, as far as like finding a function, just solve this for v, and you get v equals 3t. This is a linear function, you'll notice, with a slope of 3. So when we go to our next graph, our velocity graph, right, when t is 0, the velocity is 0, started from rest. Again, that's just this example. We'll make these match up. Sometime later, the velocity is some positive number here. We don't know this. Right? Linear function with a slope of 3. Now, where you put this point here, these are just sketches. You can put it anywhere you want, really, as long as it's positive up here somewhere. But keep in mind that now we've kind of set a scale. So this distance is 3, 1.5 would be about here, 6 would be about here, and so forth. So the coordinates of this point, right here on the end, this is the point t, and the velocity that goes with that point, v. But again, that v is equal to 3t. Okay. Now, going from velocity graphs to position graphs. So keep in mind, right, what is velocity, at least average velocity, is delta x over delta t. This can be quite easily rearranged. So your delta x is velocity times delta t. And again, the important thing to recognize, I'll do this in green. On this graph, velocity is this way, delta t is this way, and this product right here is an area. At the beginning of the video, I discussed why. And it doesn't matter that your velocity is not constant. So in this example, this green here is going to equal the delta x, our change in position. Now delta x is x final minus x initial. Now at t equals 0, we look here. The initial x coordinate of this car is 0. Now, we're going to use the area here, and that's a triangle. So 1/2, the base, is what we're calling t. It's this distance. Times the height is this distance. That's what we're calling v, which is equal to 3t. And that's going to give us our function here. Really, that's all there is to it now. We clean this up. This is going to read x equals 1.5t squared by the time we do 1/2 times 3. And it will work out dimensionally 2 meters. And again, the important thing is the t, do this in red. That's that distance on the graph. That's that from that equation. And then the 3t is this distance in green. That's where the 3t is coming from. It's important to realize that that green is the velocity at that time, which, follow this down, is a function itself. That's how it's calculated. There is our position function. Oops, I see that the palm rejection thing still is giving me a little trouble here. Again, I'm going to turn that off right after this, or try to figure out how to work it without it. Anyway, that function is quadratic, opens up. So again, this is meant to be kind of a fundamental video of how to go from acceleration to velocity functions. You do that using area. Then how to go from velocity to position. Again, you do that using area. It's a fundamental video, which is why I avoided terminology and stuff from calculus. But again, if you're in a calculus class, these are integrations going from acceleration to velocity and then velocity to position. If you're not in a calculus class, these are area under curves. That's true regardless of your mathematics level. And here are examples to do it without using language from calculus. So anyway, I hope that this video gives you a better understanding of how to go from acceleration to velocity to position functions. Have a great day.